There are a lot of properties of sequences that you have probably learned, or at least come to assume from a calculus course, but you surely never proved there. Some of these properties are related to the order relation. Those we'll deal with in a future video. For today, we'll deal with those properties that relate to the algebraic operations, where you take two sequences and you add or multiply them or subtract or divide term by term. So in particular, this first result says that if you take two sequences that converge, then so does their sum. You just simply add the two limits. Let's prove this. Our proof will look probably familiar because we did something which used the same ideas in an earlier video. We start our proof the most common way that analysis proofs start, by saying let epsilon be positive. By the first assumption, there exists an n such that all terms a little n lie within epsilon over 2 of a whenever little n is bigger than capital N. And by the second hypothesis, there is an n prime such that the terms Bn all lie within epsilon over 2 of b whenever n is bigger than capital N prime. Now, whenever little n is bigger than the maximum of capital N and capital N prime, both of the above bounds hold. So by the triangle inequality, you get this bound for an plus bn, and the right-hand side is less than epsilon over 2 plus epsilon over 2, which is epsilon. Then that's all there is to the proof. Now we can do the same thing for multiplying two sequences term by term. The argument takes just a little bit more care. Once again, we start by supposing we're given a positive number epsilon. For all little n, we can use the triangle inequality to show how close AN/BN is to AB. Then you need to think a little bit about why the terms on the right-hand side can be made less than epsilon, simply by making little n sufficiently large. So we've got two terms on the right-hand side. Let's make both of them less than epsilon over 2. For the first term on the right-hand side, I've highlighted it. Recall that all the terms an are bounded by some positive constant m. I did that in the previous video. Now you can choose n such that Bn is within epsilon over 2m of b whenever little n is bigger than capital N. This will take care of the highlighted term in purple. And now the other term works pretty much the same way. We take a number capital M prime, which is a positive bound for b. I can't just take absolute value of b, because in the next step I'm going to be dividing by this, so I need it to be strictly positive. That's why I take the maximum here. But all I really care about is the positive number which bounds b. I could have explicitly written something like this for the previous step when I chose my m in the previous paragraph. As before, choose n prime such that an is within epsilon over 2m prime of a whenever n is bigger than capital N prime. This gives me the desired bound for the second term on the right, which I've highlighted. Now I have both of the terms I want to be less than epsilon over 2. The total is epsilon, so I have that the absolute value of AN/BN minus AB is less than epsilon whenever little n is bigger than the maximum of capital N and capital N prime. This is what I need. I've completed the proof for multiplying two sequences term by term. If the individual sequences converge, so does their product. You just multiply their limits. Now, dividing two sequences term by term is a little more tricky. So I'll go through this argument in about 3 steps. My hypothesis is that An converges to A, Bn converges to B, which is a non-zero limit. I need that in order to be able to divide by B. And I'm also going to assume that Bn is non-zero. Under all these assumptions, the quotient An over Bn converges to A over B. You just take limits, top and bottom. The first step is showing that the sequence 1 over Bn is bounded. To get there, let me point out that Bn is within some small distance of B for n sufficiently large, namely within a distance of absolute value of B over 2, which of course is a positive number. For all such little n, we have this lower bound for the absolute value of Bn, found by the second formulation of the triangle inequality. And the right-hand side is at least absolute value of B over 2. So that gives me a lower bound for Bn, which is an upper bound that I want for 1 over Bn. That only applies for little n bigger than or equal to capital N. That gives us a bound for 1 over Bn, which holds for all but the first few terms. But for those first few terms, just list their size separately and take the maximum to get an upper bound that works for 1 over Bn in the general case. And that's the first step. And the second step is to show that the sequence 1 over Bn converges to 1 over B. So let epsilon be positive. Choose capital N prime such that for little n bigger than capital N prime, Bn is within this small positive distance of B. The distance required is absolute value of B times epsilon over m. Now we find that 1 over Bn is within epsilon of 1 over B whenever little n is bigger than capital N prime. This is just algebra here. You can check my work. The last step is just think of division by Bn as multiplication by 1 over Bn. Then use the previous theorem for multiplying limits. And that's the proof.